As the Earth is heated by the sun, it produces lots of warm, moist air. Warm air rises. As it gains height, the moisture cools and condenses to form clouds. These clouds grow and merge into larger ones, rising all the time. Some of the water drops become too heavy for the updraft of air to lift and fall as rain. Are lifted by powerful air currents high into the cold upper regions, where they freeze into tiny crystals of ice. As the cloud hits the base of the stratosphere, it spreads out sideways to form the anvil shape typical of thunderclouds.
The clouds that make lightning are the largest clouds in the atmosphere. A big active cumulonimbus cloud is about as wide as it is deep, and they generate long anvils which extend horizontally in the prevailing wind aloft.
Some ice crystals build in size to form small hailstones. Scientists believe that as these hailstones fall back through the rising ice crystals, millions of tiny collisions occur. These collisions build up an electric charge, which is stored in the cloud like a battery.
A cloud is very much like a battery, but a battery with a much higher voltage than your typical flashlight battery. Not 1.5 volts, but 100 million volts.
But what scientists don't know is exactly how this electric charge generates lightning.
What remains a major meteorological mystery is how it is that ice particle collisions result in the generation of lightning. We're very much in the Middle Ages on that problem.
As the Earth rotates, the thermosphere is exposed to highly energetic ultraviolet and X-ray solar radiation that ionize the atomic oxygen and nitrogen in the thermosphere. These charged atoms form a layer of plasma called the ionosphere. The ionization of atoms can extend down as far as the mesosphere. However, these upper atmospheric layers are still mostly neutral, with only 1 in a million particles becoming charged daily. The density of this ionosphere layer cycles daily. At night, the ionosphere diminishes as the sun's radiation ceases to interact with the atoms in the thermosphere. However, there are still small amounts of charged atoms caused by cosmic radiation at night. A unique property of this ionized atmospheric layer is that it reflects shortwave radio waves, enabling communication over great distances by bouncing signals off the ionosphere. However, variability of the ionosphere can disrupt communication. Solar storms is one such variable that can enhance this layer, even shutting down communication between ground stations and satellites. Solar storms can also send highly energetic particles, mostly electrons, along Earth's magnetic field lines into the upper atmosphere at the poles. Here, they interact with oxygen and nitrogen, causing formation of auroras. Auroras are formed when an energetic electron strikes an atom and one of the atom's electrons jumps to a higher energy level. When the electron returns to a lower energy level, energy is released, often in the visible light region of the electromagnetic spectrum. A deep red aurora is caused by the excitation of nitrogen atoms. Excited oxygen atoms create a green aurora at lower altitudes and a red aurora at high altitudes. A small amount of solar particles constantly precipitate from the magnetosphere, forming a background aurora that can be seen from space. NASA's AIM and Themis missions have provided valuable information about Earth's upper atmosphere. NASA's RBSP and MMS missions study the interactions at the upper atmosphere and the magnetosphere from space weather effects.